Well, looks like we can start. Welcome back, everyone. Let me bring back those announcements. Oh, they're off center. Let me try again. There it goes. So we have our seventh quiz that's due today. And our week, we're getting through these three different sections here. It's kind of a little bit off balance. We're nearly done with section 5.3. 5.4 is very, very short. And so we might end up on 5.5 today, but as usual, we're not going to try to rush it. If we have to take extra time completing that section, we'll take that extra time. Also, our second exam is coming up. And like we were mentioning earlier, we scroll through here. The content for our second exam goes through these particular sections. And I'll have extra information to take a look at when we come back on Thursday's class. But so far, this is what we have for our support material. And if you click on this document, this one's kind of new for our exam one. I didn't put this on there. But if you click on it, it's just a roundup of interesting things that you ought to have memorized, ready to go for the exam. It's on a section by section basis, and it's kind of wordy, but for example, in section 2.4, the takeaway is we need to know about the existence of that formula and that formula there. So really, that's the whole punchline. You could really condense this very, very tiny if you're going to put it on, say, a note card. Then let's see, going through these, other interesting formulas are things like slope-intercept form, point-slope form, quadratic equation, and so on. So I'd say this would be a good document to come through. So you're not looking at every single one of the lectures, trying to find that specific formula. Come just to this section right here. It's all in one nice little spot. Well, that's my announcements at the moment, folks. Any questions before we go back to section 5.3? Okay. Oh, one more thing I forgot to mention. We're also doing the thing with our ALEKS homework system, just like we did with exam one. All the due dates were really just about pacing. And so what I've done is I've taken every single section in this list right here, and all the due dates have been extended to the day after the exam, which would be October 18th. So you should be able to go into any one of those sections unless they're completed, then you wouldn't have to worry about that. If you, for some reason, want to get caught up on other sections, I shouldn't say for some reason, that's a good idea. If you want to get caught up on other sections, let me know, and I'll be very happy to go into the system and give an extension on any other section, maybe 3.7 or something like that. But these are the ones to definitely focus on for the second exam. And so if you decide to primarily focus on those problems, that would be a good strategy for this point in the class. Well, we'll talk about the second exam a little bit more on Thursday's class. But any last questions, folks, before we jump back in? Okay, well, here's where we left off. Well, we left off on example 6, the last one in section 5.3. But before we look at that example, we should look at this one once again. We're going to solve polynomial inequalities. And what that means is we'll have a less than sign or a greater than or equal sign on one side of the inequality. But to solve the inequality, it's really this right here that you want. If you can show, say, a rough sketch of the graph where all the real zeros are, then you're in really good shape for solving the inequality instantly. So the run through with this problem was, it was in a nice factored form. We found the zeros, and we also indicated their multiplicities. Whenever there was an even multiplicity, like this one with multiplicity 2 or the one with multiplicity 4, the graph is going to bounce off the x-axis and still stay on the same side. So here with our 0 of 0 had multiplicity 2, so it came around and just was repelled off the graph. The one with multiplicity 4 at 9/2 did the same thing. But this one at multiplicity 1, this was at -7/3, it went through the graph. So knowing the zeros and the multiplicities is going to help us solve inequalities. But there's still one more special ingredient here. We had to know it was increasing on the right and decreasing on the left. So the other document you'd probably want to have pulled up is this one here about power functions. So this told us where the ultimate arrows were on the far left and the far right as well to give us the full graph right here. So we're going to try this all again. Really, it's an opportunity for us to just practice graphing these things, which is a long process on its own. And after we graph them, we'll also solve these things right here. So example 6 is our last one of this set of the notes. All it says is solve the inequalities. There's multiple methods for doing this, but we'll try to do it by plotting. Also, the definition here is really nothing fancy. It's saying if you have a polynomial inequality of degree n, that would mean your leading coefficient cannot be zero. So power n survives on this term right here. And instead of having equality, we'll have either a greater than, less than, or maybe less than or equals, or greater than or equals. Said that backwards. That one's the greater than or equals. That one's the less than or equals. Well, any questions, folks, before we give this one a try? Okay, let's give this one a go. And here's the first thing we want to take a look at. The polynomial is in really great shape. We want to have a variable and then a constant, either plus or minus is just fine. But we don't want any coefficient on that variable. So it should just be x, not a 3x, not a 2x or anything like that. So this is really the problem right here. Before I even begin, I want to correct that term. I want x to come first. I don't want a negative x there. So we're going to write this as x minus 5. So in the scratch work, we're pretty much just taking 5 minus x and rewriting it as a negative x minus 5. The negative side can just be factored out, which means you're just dividing everything by -1. So here's our new inequality. It's going to start with the negative sign coming from this one here. I'm just going to move it all the way to the left. Then it'll be x plus 4, x plus 9, and now x minus 5 is greater than 0. Only highlighting that in yellow just to show we corrected that term, and this is the format we would prefer. Once we get to this stage, here's the next thing we can say. The leading coefficient I'll often abbreviate coefficient to just coef, since that's a really long word. Well, if we expanded all of this, FOILed out multiple times, we'd eventually come up with an x times an x times an x. So we'll have an x cubed multiplied by that -1 right there. Really the thing that's in front of all those parentheses, that is going to be your leading coefficient. So we get a -1, and it's going to be less than 0. I only wrote this less than 0 here because I'm thinking of, let me see if I can pull this out in a nicer way. I'm thinking of this graph right here. K less than 0 is now putting us into this situation. We just have to decide, is the degree even, so the arrows are going in the same direction, or is it odd, so the arrows are split up? Anyone see what the degree should be on this one? Exactly, we have degree 3, so the result is odd in this case. Our arrows are going to be doing this now. So let's write this in. Degree of f. I often just abbreviate the degree of f as deg for degree of f with parentheses in that way. And really, we're just counting these off. It'd be 1 from that parenthesis, plus 1 from that parenthesis. If that was x cubed there, I would have said plus 3 instead. And then plus 1 coming out of that location. So we have degree 3, it's of odd degree. And then once again, our arrows ought to do this when we go to graph. The next thing we want is the real zeros. Coming back over here, here's how this will go. Let me put this in kind of a bullet point format to just show each part of this process. So this is the third part we have to analyze. The real zeros are, this is always weird to say, the real zeros. That's always fully synonymous with the x-intercepts. So that's the reason why this is a terminology that comes up a lot. So the real zeros, we can come up here. We're just going to take the opposite of the constant term. Put in -4 for x, and we get a 0. So that's our first one. -9 will give us a 0 as well. And a +5 right here will give us our next 0. Now the degrees on all of these parentheses are all degree 1. So we'll say for each one of these, there's a multiplicity. I use mult for multiplicity of 1 for every single one. That means when we go through -4, -9, and 5, we'll actually cross on the graph. We won't bounce off like if it would have been an even multiplicity. So with all that information there, we're ready to come back to the original question, this up here, and solve the inequality. Any questions, folks, about these 3 bullet points so far? Okay, so here's our fastest possible graph. It doesn't have to be pretty. It just has to have the right qualitative information. First, I'll put down the zeros. They are at -4, -9, and 5. So 1, 2, 3, 4. Here's our first one. And now when I plot this zero, let me zoom in a bit. I'm going to use something a little bit different this time. A greater than sign implies, if I was thinking of interval notation and the graph of the solution set, there'd be an open circle on my real axis graph. So I'm going to put an open circle right here, which looks a little bit odd at the moment, but that's just to help me with the interval notation, matching up with that inequality right here. If that was a greater than or equals, I would have put a solid circle instead. So now let's go to the next one. It's at -9. So -5, 6, 7, 8. At -9 here, another open circle. And the last one's at +5. 1, 2, 3, 4, 5. Third open circle here. And now let's check this out once more time, just for a reminder. Leading coefficient was negative. That's this first bullet point. The degree is odd of 3. That's the second bullet point. So our graph is essentially doing this. All the multiplicities are 1. So when we go to graph, we'll be passing through. So our graph finally looks like this in the end. Comes through -9 in this way, through -4, and I forgot to put a number there. Not completely required, but it just helps the eyes on the next step. And then it comes through in this way. So there's our really, really rough sketch of the graph. But at this stage, we are so close to done. We just have to say, what are the answers? What are the intervals we actually want? We're going back to this right here. If it says we want all of this done to be greater than 0, would you say that's where the curve is above the x-axis or below the x-axis? Exactly, greater than 0 is implying above the x-axis. So let's say this right here. We want intervals where the graph is above the x-axis. If that was a less than, we would have said below instead. So the above is only because of the greater than right there. Going to take off that note that we did for factoring, just so it doesn't get conflated with the comment above here. Let's use green for our official answer. So we want everything to be positive. Let me extend my axis going this way. We're positive to the left of -9, so all of this can be part of our solution set. It goes to the left forever. Our curve is never going to turn down again, so it's going off to -infinity. Here we have a void. There's no solutions. The curve is below, but here it's once again above. So we have solutions going from -4 all the way to the +5 right there. So finally, last thing to do is state our answer. I'll write out like this: the solution set, the set of all the solutions, reading left from right will be from -infinity all the way up to that -9 there. We have to use parentheses because of the strict inequality. It's just a greater than we're looking for. Then a union symbol and grab this set. Union from -4 to +5. So we did it, folks. That's our process of solving the inequality. Really, it was just an opportunity to graph these a little bit more. This is really only our second one we've graphed, so that helps us out there. And for free, we have a related topic. If you could graph it, you can solve the inequality essentially instantly. Well, any comments or questions, folks, getting through this one? Okay, this is really pulling together a lot of material, a lot of ideas, really from section 5.1 all the way through everything, example 1 through 5 of section 5.3. So think of this as one big kind of a review problem in a certain sense. Let's try this again just to get some practice going on it. So here's our part B. Same kind of deal. It's a wild-looking polynomial. There's a difference here of less than or equal to 0. But looking through this, let's take a look at our terms. It goes x and then minus, x minus, x minus. That means we're in good shape. watch out for these, like a 5 minus x. You always want to correct that, or else we may not know what the leading coefficient is. And if we don't know the leading coefficient, we may not know which way the arrows are going on the end behavior of the graph. So this one is all set up. It's in good shape. We can immediately now say the leading coefficient is equal to, it would just be that -3 right here. So -3 goes in. It's less than 0. And so that means, well, we're going to have some expectation for the end behavior. But until we find out the degree of this function, it's not completely clear. I'm calling all the functions f. So my f of x, or f, is really just that thing right there. We need its degree. But we can analyze it in the same kind of way. From right here by the red dot, there's a contribution of 1 to the degree, because the power on that x is 1. But what about over here? What's the contribution to the degree on that factor? Exactly, ought to be 2. Not just because of that x, because that whole group is squared. If you were to FOIL all that out, you're going to get an x squared. So we have a contribution of 2 towards that degree. Then over here, a contribution of 1. So this time we're of even degree, because it's degree 4, and the leading coefficient's negative. Both of the arrows are going to be turning down, like we see on this graph by the red dot. So that helps us out with some expectations. Next, we need our zeros of this thing. I'll just read them off going left to right like before. The real zeros. First one is going to be a +5, found by right where that red dot is. This one has a multiplicity 1. When we go to this one, something new happens. The 0 itself is 2, but the multiplicity, I forgot which one gets a T and which one's an L. Let me try again. Multiplicity is 2 on this one. That means we need to be very wary of that one. Here's where it's going to be the so-called touch point. It'll touch the x-axis and then rebound off. Maybe like this, or maybe like this. We'll have to see where it falls and where it goes. But for anything that's an even degree, it's a good reminder that this one will be a touch point. Then finally, last one. So I get that blue back. We have here another 0 of 7. This one has multiplicity 1 as well. So we expect it to cross the x-axis at that value. So that's really the whole work on this. Say what the leading coefficient is, the degree, the zeros, consult some graphs like this one here. And now we're ready to start solving this whole thing. Any questions at all, folks, with getting those 3 bullet points down? Okay, let's see how this one goes. So first, we'll throw in our graph. Next, we want the zeros. That's where a lot of information is happening. So 1 at 5. But this time, right at 5, I'm going to change this one up. When it says less than or equal to 0, I'm not going to use the open circle like we did above here. This one we ought to make solid, since that value at 5 is going to be a solution this time. So I'll go right at 5, a solid dot just like that. Then next one, at 2, we have multiplicity 2. So another solid dot here. And finally, we have a point at 6 and 7. So that's our final one right here. Well, let's be really careful with this location, because once again, it's the touch point. But the rest of the graph can now be sketched pretty quickly. I'll use black again, just like in the last problem. It has to start from below. It comes up. Because this is one is a touch point, it comes out like that. The rest of them are cross points. They have odd degree, degree 1. So it's going to just cross here, and then go in those 2 directions. Double check that we have the right behavior, like we see right here. Double check your multiplicities where the zeros are. but looks like we've got the right graph. Any questions so far, folks, on the graphing phase? Okay, well, we have some demands for this graph. To find our solution set, that less than or equal to 0 says we want where the graph is below the x-axis or where it actually is on the x-axis. I'll say here, we want the regions below. We're only saying below because of the less than or equals on this one, the x-axis. So let's go and start highlighting regions below the x-axis. Well, they start here and they're all the way to the left. It's always going to be below the x-axis in this direction. So I'll start shading at from negative infinity all the way to that 2 with a solid dot. So we'll include the 2 this time with a bracket. Then here, well, it's still below the x-axis. So we just keep on shading. Sometimes these can look a little bit unusual, but below the x-axis or actually hitting the x-axis is appropriate on this one. Plug 2 inside here, and you just get 0 is less than or equal to 0. Weird statement, but it is true. From 5 to 7, that's going to be a hole in our region where we're trying to find values, because here we're above the x-axis. We wanted it below, but starting off at 7 and going to the right forever towards infinity, it's below the x-axis again. That's hard to say really fast. And so that's our graph so far. All we need to do is take that number line, put it down in interval notation. So our answer this time is solution set comes out as negative infinity. This time, when we go at 2, we don't really stop this time. It's everything going up to 2, including 2, and going past 2. We just stop right at this 5 right here. So it's going from negative infinity all the way to 5 with a bracket. There's really no value that was missing there. And so we write that as one entire interval. That's really tricky, but on the graph, it's not as bad. It just goes right through. Then we have a region that's missing here. And we'll pick up union 7 to infinity with a bracket on 7. So that's finally our solution set on this one here. Any questions at all, folks, on getting to the end stage? Okay, again, like I mentioned, these feel like long review problems because, well, it definitely is. Just about everything from 5.1 to examples 5 and 5.3 was used to get to this point. They're kind of long questions, so on our real exam, I'd probably only do 1 tops. But before we try another, any questions at all? Okay, we really ought to do 1 more. These are kind of exciting problems. They take a little bit of time to get through. I have a feeling that in ALEKS, these are kind of tricky. So if you feel like they're not being the funnest problems, come back here on the notes, and we've solved just about anything that's terrible that could happen in ALEKS. Part C is the last terrible one. It's the challenge of the set. But honestly, it's not too bad. We just have to be careful as we go through it. I did want to make 1 small change on this problem. So just to get some more variety, I've noticed all of our leading coefficients were negative. So I'm going to put a negative right here. I want a positive leading coefficient on the end of the day. So sorry for this small change, but I think it'll make the notes a little bit better. My change is from a positive 2 to a negative 2 right there in red. Okay, well, let's try this out. First thing we look at is we want to have things in a nice format. It should be a variable x and then a constant term, much like this one with x minus 5, x minus 2, quantity squared, x minus 7. That's terrific. But in this problem, I would say this is the nastiest part right here. 8 minus x quantity cubed is not helpful for us if we're graphing this thing. We would rather have an x minus 8. So we need to factor a -1 from that group in yellow. Factoring a -1 is kind of tricky on this, but here's what the punchline would look like. You could take 8 minus x to the power 3. These are the kinds of steps that you really only want to do once, and then after you've seen it, you just use the trick. I'm factoring out a negative inside the group like this. So I have a factor of -1 out of 8 minus x. So now we can call it x minus 8. Now the power of 3 distributes to both of the factors. This will turn into -1 to the power of 3, x minus 8 to the power of 3. -1 cubed is just -1 times -1 times -1, resulting in negative x minus 8 to the power of 3. But this is essentially the trick. If you want to put this as an x minus 8, an extra negative sign comes out. So our problem will turn into the -2 we threw in there. 8 minus x quantity cubed is going to be, oh, I need a little bit of extra space here. This is going to be x minus 8 cubed. And that's the -1 that we get as extra right here. So now we have a leading coefficient that's positive. This term has been corrected. I'll highlight that -1 as well to say that was the result of pulling out the negative. And everything else was just fine. X squared plus 9, x squared minus 25. Well, maybe it's not all just fine. This one we cannot factor without the use of complex numbers. We're only looking for the real zeros. So we're not too worried about complex zeros if we're just graphing this and solving an inequality. But that one does factor. That one can be factored as a difference of squares. We'll get 2 real zeros, a +5 and a -5. So we should do one more step on this one. On the left, this is a +2 times 8, x minus 8 cubed, times x squared plus 9. And for x squared minus 25, so split as x plus 5 times x minus 5. And the whole thing is greater than or equal to 0. So that's what we'll be solving on this problem here. Well, any questions, folks, with fixing the original inequality? Okay, if we're happy with the fix, here's what we'll do next. Just like before, we want a leading coefficient, degree, and the real zeros. So there's our leading coefficient there. It's a +2. So leading coefficient equals 2, which is positive. Because we have a positive leading coefficient on this little cheat sheet here, we'll switch to this row where k is bigger than 0. Next, we need to know the degree. This one's a little bit tricky as well. So the degree of the function f. By the function f, I'm just referring to just the left-hand side of the inequality. And here's how we can figure it out. From right here, we have a contribution of 3 because of the power 3, plus our non-factorable or irreducible polynomial. Well, that has a power 2 there, so we get a contribution of 2, plus power 1 and power 1, so 1 plus 1. Or we might have said plus 2 because of the power 2 there. But at the end of the day, it looks like we're having degree of 5, 7. So we're of odd degree this time. So back to the cheat sheet. That means we'll be using this end behavior right here. The arrows are going to be going in those directions. Last thing, the real zeros are, and let's just list these out. Starting from left to right, first one's going to be 8 with multiplicity 3. Because it's an odd multiplicity, this will be a cross point. I'll just say cross right here, just for a reminder. On this one, we don't have any real zeros. The zeros would have been -3i and +3i. We'll see how to find those in our upcoming section, 5.5. But from here, we do get some new stuff. This one will be a -1, or excuse me, a -5, has multiplicity 1. So this will be a cross point as well. And now +5. Multiplicity 1, once again, so another cross point. So these points are nice. There won't be any weird behavior where we saw the touch points in the last example. So now we're just really stitching everything together in these 3 bullet points. Let's start with the zeros. They are at 1, 2, 3, 4, 5 to the left, so -5 here. 1, 2, 3, 4, 5 to the right, and 6, 7, 8. Now, next thing to look at is the actual inequality itself, it's greater than or equal to 0. Because of the or equal to 0 part, we'll use solid dots right at these locations. Think of in green is, what's happening in green is I'm really just trying to graph something along these lines. I'm pretending it's a real number line, but I'm only bringing this axis back so I can see the curve and to just decide what parts of that real number line get shaded overall. So that's the reason of using solid dots versus on part A, we had to use open dots because of the because of the greater than sign. So now putting the graph in, let's remind ourselves, the curve should be going like this right here. So it's falling to the left, rising to the right. All the points are cross points. So if we do something that does about that shape, we're in good stage or in good shape. I just want to make the color consistent. So let me try one more time. I think we use black on all the other ones. Last thing to do is look at the direction. If it's a greater than, we want all the regions where the curve is above the x-axis to match up with a greater than there. So this region from -5 to +5 would be part of it. Then starting at 8 and going to the right forever towards +infinity, that's the last region. So we've got it, folks. Our solution set is from -5 to +5 with brackets, union, bracket from 8, all the way over to +infinity with a parenthesis just because that one was in infinity. So that's the process. Any questions at all, folks, on getting through those inequalities there? Okay, well, congratulations. I think this section is definitely a tougher section. 5.4, we take a bit of a break, and 5.5, in my opinion, is not as bad. It looks scarier at first, but when you go through these notes and try to look through the information again, I think you'll find that 5.3, there's really a lot of stuff going on inside of it. So it's nice to bake through that section there. Next thing we'll be looking at is division of polynomials. Once this saves, there it goes. Any comments or questions at all, folks, before we go to that next section? Okay, well, congratulations again. This one was a pretty tough section to get through. And now we're in section 5.4, dividing polynomials. Like I mentioned earlier, this section is not really that long. It starts off right away with the good old division algorithm. So my thought with these notes was, we're going to be dividing polynomials like, say, right here. But before we even do that, the division algorithm is actually a big part of these kinds of questions. Let's do a warm-up problem right here and just kind of absorb what the division algorithm is even saying. I have a division that I wrote out here that seemed kind of fun for today. We'll do 572 divide by 23. So in doing this kind of deal, we won't really consider that a polynomial along division, but in a certain sense, you really could, because you could say the degree of the polynomial in the numerator is 0, the degree of the polynomial in the denominator is 0. They're real polynomials in their own right. So if we're using the division algorithm, first thing we want to decide is, what is the actual divisor? That'll just be the thing in the denominator, the 23 right here. And that would be the d of x that we see right here on the first equation, and also right here on the second equation. So we have a divisor, and if we're going to come up with an answer, we essentially just take that divisor of 23 and throw it in right here. Next thing we take is the 572. Our author doesn't say what that is in the land of, say, divisors, quotients, and remainders. But if you're curious, the 572 is called the dividend. I don't know who came up with that. Probably someone worried about money more than anything. That's called the dividend. So take the numerator or the dividend and throw it inside here. That's where our division algorithm is going to begin. So that's our setup so far. Next thing we do is, well, we just wonder how many times will 23 go into 5? 0 times, so we don't do anything there. We wonder how many times 23 will go into 57 at most. Any values that folks would put there for 57? Probably 2, right? 23 is like 25, and 3 times it would be about 75-ish. So we're expecting 2. Once we place that 2 there, this is where the action, whether we're doing ordinary numbers or polynomials, it's all completely the same. So after we solve this one, we could put this side by side on our next problem and just track the actual steps we're taking on both problems. The 2 comes down here and it multiplies. That's going to give us a 46. Next thing we do is we come down here and we alternate the sign. It's coming in as a positive 46. Now it'll be a negative 46. And that little bar below is just saying tally. Only those first 2 digits, or this column here. We're going to get a 1, 1. So 2 carries down. And now we need another value. For 1, 1, 2, if it was 25, it'd be about 4, right? So 4 should do the job this time as well. Let's give it a try. 4 by 3 is 12. Carry the 1. 4 by 2 is 8. Plus 1 is 9. Then we'll subtract this quantity. We should get 20 exactly here. Because the 20 is less than 23, this is where we would stop. And what would you all call the 20 at this stage? It's got to be the remainder, absolutely. Let's use maybe green for remainder. So the remainder goes here. And in our equations, it also goes right here and right here. So that's where our remainder fills in. Also, the 24, that's our quotient. It's essentially the answer after long division once we bring it together with the remainder. So this 24, we're looking at the 2 equations below. It'll go in this location and in this location. Got to highlight that divisor there in yellow. So back to our problem. I'm going to write our answer in the first equation format. 572 divided by 23 is a quotient of 24 plus a remainder of 20. But notice that remainder of 20 is still divided by the divisor. So we'll put this over 23. So although there was no variables x there, we did it, folks. This is exactly what we're going to be doing, whether it's polynomials or ordinary integers. And there's 2 equations. That's kind of rude in a certain sense, but really they both have value. In section 5.5, we're going to be solving polynomial equations. The best way to solve an equation is to factor it. So that's the purpose of that equation over here. So I'll say this is useful for equation solving. If your problem is not just about long division, if you're really trying to solve an equation, you're probably going to use this format right here and hope that your remainder is 0, so you actually have a factorization. In our problem, if we put it in that format, we would say the number 572 is equal to, well, first it'll be the divisor. So we'll take our divisor of 23. Then it multiplies the quotient. Our quotient is that value of 24. So 24 goes in. Then plus just the remainder of 20. And that's the related equation. So we could either format our answer in this way or that way below. Essentially, the way you get to one or the other is you take the 23, they'll multiply here, like we have it below there. And when it multiplies over here, it clears the denominator. And that's why we're seeing just the 20 in that location. Well, we did it, folks. That was our first long division. I have 4 more to go on these notes. But any questions or comments first? Okay, well, this is essentially just one big analogy. Let me take a screenshot here. Now let's try this all out again. So think of this again as the warm-up. Division algorithm is here, just copy and pasted. And this is what a real ALEKS question is going to look like. They tell us to divide, makes sense. There's the division symbol right there. So we're definitely dividing. And then we'll state quotient and remainder. So first, let me drop this right over here. I'll delete it in a moment, but it's comforting to see something we're familiar with when we're about to do something new. Now on this one right here, we'll start off just like we did before with a big long division symbol. Any volunteers for what should go right here by the red dot? In other words, what would you say the divisor is?
X minus 2.
Exactly. So divisor x minus 2 goes into that location. Next thing, the dividend. That always sounds weird. The dividend was 572 on the prior problem. For us, it's this, 12x squared. So we'll write it in this location, plus 10x plus 3. So that goes inside, I guess you could call that the box and under the long division symbol there. Now, what we did when we started off was we said 23 doesn't go into 5. So we moved over a digit. Then we said 23 would go into 57 twice, and we brought that number 2 up. For us, this is what it's going to look like. I'm going to do some of these computations in this pencil tool right here. I'll delete them after we do them, just so that the notes don't get too busy. If you ever want to see that scratch work, you can go to the video to this portion of the example. So first thing we do is we take this right here. We divide our x into the leading coefficient of 12x squared. And that would be our scratch work to start. X dividing into 12x squared, much like the 23 dividing into 57. When we do this division, we're just going to get a 12x. And we take that 12x and copy it up right here. What we're forming right now is part of the quotient. So might as well use blue at this stage. 12x goes into that location. Does that make sense, folks, on obtaining that 12x there? Okay, so the pattern of attack is take that, the leading coefficient there, divide it into the leading coefficient here. That's where the scratch work went. And you're definitely in business at that stage. So just like over here, once we got the 2, we took it and we multiplied right here, and that gave us the 46. That's exactly what we need to do next. We need to take this 12x, multiply it to the x, and multiply it to the -2. It's still a multiplication step, but now it's also using the distributive law all at the same time. So visualizing the arrows, 12x times x gives us a 12x squared. Notice that's the same quantity in this column. That means we're on the right track. They have to be exactly the same. If I got 11x squared or 11x, I'd have the wrong thing, and I need to start over with getting that number in blue. Then 12x multiplies the -2. We'll get minus 24x. And we're off to a great start. So we've done the step where we took the 2, multiplied it by the 23, and got a result in. This will be the next step. We change the sign of whatever we produced right under here. So this is a positive 12x squared. I'm going to change it to a negative 12x squared. This was negative, so I'll change this one to positive. I'll put my sign changes in purple, so if you come back to the notes, you'll know I made that sign change right at this step. Next, we throw in a tally bar. And when we were at this stage, all we did was we took 57 minus 46. This time, we're taking 12x squared plus 10x minus 12x squared plus 24x. But really, we're just going across columns. 12x squared minus 12x squared is 0 by design. We wanted 0 there. Over on the next column, 10x plus 24x takes us to 34x. Now, the arrow down just said carry information down to the next step. So our arrow down will look like this, plus 3. Now it's rinse and repeat. We have a new thing, 34x plus 3. It's as if this doesn't matter anymore, the original dividend. And back to the same process. Any questions, folks, before we run it through the division second step? Okay, is it making sense how it goes together in this weird new landscape? Awesome, I'm glad to hear it. It always looks so different, but if you do these side by side, that's a good way to convince yourself it's really the same kind of thing. It just has x's that we have to deal with. So now our next step is we take x again, and this time we're dividing it into the new leading coefficient, which is 34x. So I'll put a 34x here in the scratch work, divide by x, and we get a 34. That's the next piece of our dividend. So take this, because it's positive, we'll put plus 34 up above. Next thing is the multiplication step. 34 multiplies here, so that's going to be a 34x. It has to multiply here, so that's going to be a negative 64. But then, before we do anything at all, now we change the signs. So from here, that goes from positive to negative. And from here, it's now negative to positive. Finally, we'll do a tally. So here it is. X's disappear in this column, and we have 3 plus 64, giving us a value of 67. But that's now a remainder. At this stage, well, our work right here is complete, but we still have to state our answers. Yeah, go ahead.
Would it be 68?
Oh, absolutely. Thanks for spotting that. Kind of sucks to get right here and mess up that multiplication. So with a quick correction, this was 68 in that location. So now we're up to a 71. Thanks for spotting that there. Other questions so far or comments? Okay. Oh, and I forgot. This is our remainder, so let's put it in green. Over here, we stopped. The only reason we stopped was 23 exceeds 20, and we weren't going for a decimal answer. Over here, we stopped because 71 is of degree 0. You could put in an x times 0 if you really wanted to, and that's why it has a 0 degree. This x here is a degree 1, and because it's of higher degree, we stopped right here. So let's state our answer. We'll say here, the quotient is the 12x plus 34, and the remainder came out as just a 71 on this problem here. It means x minus 2 didn't divide evenly, but that's okay. We have quotient and remainder to know what about happens after division. Well, any questions at all, folks, on getting through this work here? Okay, well, let's try it again. Only way this gets a little bit nastier is if maybe the divisor here gets more involved, or the dividend here gets more involved as well. But really, there'll never be anything more involved than something like this one. This one's just for the sake of practice. So let's practice the division algorithm one more time. So new polynomial long division. Really, only thing that's truly new in this problem is this new format of the answer. Occasionally, Alex asks for just quotient and remainder. That's all they want. But sometimes they want your answer in this format, the quotient plus the remainder divided by the divisor. In a certain sense, that's really the better kind of answer they're going for. And we'll see why once we go through this problem. So let's start off like before. We'll take, and let me remind myself of the color coding just to keep things consistent. We'll take our divisor, x squared minus 3, and put it right here. Dividend, that's just the numerator, goes in as x power 5 minus 2x power 4 plus 3x cubed. And now I have a big problem. I have x cubes, and then I go to power 1 on x. That means, well, we have 0 copies of x squared. And this looks really weird, but 0 times x squared is the correct thing. And if you put that in right here, it will absolutely make the rest of this process a little bit easier, as strange as that sounds. Especially once we go to synthetic division, that step here becomes mandatory in our new way of doing this kind of long division. So always watch out what's happening with the powers. If there's something missing, by missing it goes 5, 4, 3, 2, excuse me, goes 5, 4, 3, skips the power 2 and then goes to power 1. You still want to plug it in, as weird as that seems. Then minus 8x plus 18. So we've got all inside there, and now it's really just running through the algorithm. Again, I'll still use these pencil tools as just essentially scratch work on the process. Think of this as your leading term here, and x power 5 is your leading term. And you're just taking x power 5 divided by x squared, getting that result of x cubed. So first thing we get is x cubed, and I'll throw it right over here. Next, we're distributing x cubed through, and this is going to look a little bit weird as well. Multiplying here to here is x power 5. That's not too bad. I would put it right here. And multiplying here to here is minus 3x cubed. I would encourage you not to do this. That could cause some real problems, right? Since in this column, those are not like terms. I'm not going to get negative 5x cubed. I'm not going to get negative 5x power 4. It's best to put it way over here. So x cubed multiplies negative 3. Let's put it way out here. Minus 3x cubed. That way we're always putting things under the column that corresponds to the like terms, same powers on x's. Well, we've done the multiplication. Next thing is change our signs. So this becomes a negative x power 5. And this will turn into a positive x power 3. Let's tally these up just like before. Trying to keep these colors consistent is kind of challenging. There we go. We get nothing in this column. Here we have negative 2x power 4 copying down. And here we get 6x cubed. So plus 6 x cubed altogether. Now we can carry down some terms. 0x squared comes down. Minus 8x can come down. And you could carry everything down if you'd like, but I think those are the only two I need to carry down at this step. And now it's rinse and repeat. We have a leading coefficient here that always stays the same. That's going to be in the denominator. This one changes after every new tally bar. So negative 2x power 4 goes into this location. And our new piece of our quotient would be negative 2x squared after division. So take this piece, follow the arrows on how we divided. Up here, it's going to be minus 2x squared. Does that look right to folks so far? Okay, so with that result record above, next phase is multiplication, but we're only multiplying the new term that we produced. So this will multiply over to here. We're going to get a negative 2x power 4. They have the same sign, so we are in good shape. That means we can proceed. Next, it'll multiply over here. This is going to give us a positive 6 through those two multiplications, x squared. So I'll put it way out here, plus 6x squared. Probably didn't need to carry down the negative 8x. That was an extra term, but that's okay. We'll tally these two and then bring down everything on our next step. Oh, I did make well, not a mistake, but I did skip one thing I like to do. When you do hung division, there's so many little steps. It's a good idea to try to become extremely methodical. Always do everything in the same exact order. That way you don't get mixed up on a step and forget to do something like, say, change the signs. I've never done that, right? Let me change the signs right at this stage. This becomes a positive. And this one, which was positive, becomes negative. I'll do it this way because overwriting a positive to a negative just looks like a mess. I put in a negative sign and then just circled it to say, that's a sign I'm going to be using overall. So another tally bar, we get 0 copies of x power 4. 6x cubed comes down. 0x squared minus 6x squared, that's still just negative 6x squared. The negative 8x, positive 18, all carry down. So another rinse and repeat, and we'll be on our way with this problem here. Well, looking at how the problem stands, can anyone see what the next term should be up above here? Good call. You're taking x squared, dividing it into 6x cubed, plus 6x is our result. Then 6x multiplies here, that'll be 6x cubed. Next, 6x multiplies to here, that's going to be negative 18x. Now, again, try to do this methodical, whichever is your preferred order. I'll change the signs right here before writing the tally bar. So negative here, positive right here. Oh, and I could do that a little bit better. It's easy to take a negative sign and make it positive. There we go. Next, we tally up the results. And we're about ready to write a remainder. So no quantity of x cubes, or hang on, we're not ready to write a remainder. There's still an additional step on this. Negative 6x squared copies down. But notice the degree of that is 2, and so is the degree of our divisor. We have to go one additional step on this thing. So negative 6x squared, this is going to copy down as plus 10x, then plus 18. We've got to be close because we're running out of space. We're almost at the edge here. But let's do it one more time. X squared by the red dot divides down here. Just gives us a negative 6 overall. Then we take the negative 6, sign and all, multiply it first here. That'll be minus 6x squared. Then multiply it over to here. That's going to be positive 18. We're just about there, folks. Now we're changing the signs, this one from negative to a positive. And this positive will change to a negative right here. Now, once we tally, we have a remainder of, there's no x squares, 10x comes down, and, well, that's it. Positive 18 minus 18 results in 0. Because we still have a remainder, it tells us x squared minus 3 did not divide into that evenly. We get this result, quotient plus remainder over divisor. I mentioned earlier, sometimes this is the better way to write our answer. When we did our long division earlier, we just simply said, well, the quotient is 12x plus 34, the remainder is 71. But over here, we get the opportunity to say that this whole thing is now equal to something. This, as a division problem, is equal to the quotient of x cubed minus 2x squared plus 6x minus 6. So that was the quotient right here that we produced. We'll add to it the remainder. What's our remainder? It was that 10x. Divide by the divisor. Divisor again is the x squared minus 3 in the denominator. And that will be our answer on this one. So this is kind of a nice problem in the sense that we're not just saying what the quotient and remainder are. We're saying what the result actually is when you divide this thing. You come up with this new function right here. Well, we did, folks. That's kind of the nastiest long division we'll probably ever do in this class. Any questions or comments about it? Okay. Trouble with long division is it's a huge amount of writing, but we can't fix that.
That one thing too is
exactly. Yeah, if I made a mistake, say right here on that x cubed, all of it has to be wiped out. We start it all over. That's the worst thing to ever happen. The more you stare at this, it actually didn't depend on writing x power 5 or x cubes or x squares. None of that stuff actually mattered. The only thing that mattered in picking up this answer, where you put your x's back, is the actual coefficients, the -2, the +3s, the 6s, the 0s. Those are the only things that actually matter. And so if you ever face a situation where you have to long divide a lot, that's going to be us in section 5.5, we need to divide more efficiently so we aren't doing this so long form every single time. For that reason, let's take this problem. Not that one, but this one. And we're going to try to do it again. By that, I mean, we're going to try to do it without actually writing down this division structure and just say, what is the numerical game that you have to play to come up with quotient and come up with a remainder? So that's going to be anytime you see this, synthetic division. Synthetic division is not a requirement in this class, but for certain problems, like this one, if you divide by something of degree 1, our synthetic division process is extremely efficient. It takes about a quarter of the time of doing this thing right here. So think of this screenshot, which is just temporary, as an analogy to what we're about to do in synthetic division. So this technique is pretty unusual. And there's multiple kinds of synthetic divisions depending on how many terms are in the denominator, if it has a coefficient, what the degree is. But this will be the only context we use synthetic division. There's two terms in your denominator, and it's of degree 1, and the coefficient is also 1. So it's kind of like an all-time best case situation. First thing I'd want to highlight in synthetic division is that's right there. In a certain sense, that's the key number that we have to work with. We put a bracket, all this is kind of new, and the -2 doesn't exactly go in there. We put it in with the opposite sign. So let me just put an arrow here that says change signs. The next key element in synthetic division, again, it's not about the x squared. It's not necessarily about the 10, or excuse me, the x. It's about the numbers, positive 12, positive 10, positive 3. We put those in through here in this way, 12, 10, and 3, completely ignoring the x squared and the x. Then give it a little bit of a gap, put a bar down here, and this is where the process is about ready to begin. So the setup always starts like this. Go to the denominator, take the opposite sign, place it here in a box, pull all of your coefficients, just put them in a row going in this way. You have to be in descending order, so x squared, x. Watch out for any term that's being skipped as well. And now, here's how it starts off. The very, very first thing you do in synthetic division is you take this 12 and you immediately put it right down there. That's not too crazy as a step. And looking at our process, we did come up with the 12. So we're picking up the very first number at least going through this. Now, what did we do in the next thing? Well, once we came up with that 12, we eventually had to double it and change the sign, multiply it by -1. The sign change is already baked in when we went from the -2 to a +2. We just haven't doubled it yet to come up with the 24. But this 2, every time we go and write numbers going over here, we're always going to multiply. So if it's a +2, it'll multiply that 12 and give us a 24 and that location there. So here to here, the action is multiply. I'll just write mult for multiply. Back over here, we have a column of numbers. We have to decide what to do with that. But notice how we came up with the 34. That's just adding these two up, and that's not a coincidence in synthetic division. Every time we have a column of numbers, except for the first one, this arrow is the exceptional one, we always just add these. Really hard to write sideways. Let me give this a try. Add. So we get a value of 34 next. Noticed we did pick up a 34. It turns out writing out the 10x, 24x to get a 34x, that's just the same as 10 plus 24. That's the better way to write it because it's way fast. You're not going to be writing the variable x like 30 times or 50 times for one single long division problem. So now what happens next? Not that. Let me try again. The 2 goes over here. It still is multiplying. So 2 times 34 is going to give us 68. I got it this time. So a value of 68 goes here. And now in the new column, we just add them together just like before. We pick up a value of 71. That 71 is the remainder. So we're pretty much done. We just have to state quotient and remainder to finalize the problem. So that's the method of synthetic division. And I assure you we'll be doing quite a lot of these. So even though this is our first rodeo on this kind of process, I have one example down here. But the section 5.5 notes, this is going to be our main technique. So we'll be practicing this extensively. We still have to write our answer, but let's get rid of the long division way, where we took quite a lot of time to get through that. To resurrect our answer, here's something that people sometimes add to their diagram. It's not required, but the 12, the 10, and the 3, the 12 came from an x squared term, and the 10 came from an x term. Coming down here, the degree drops by 1. This 12 will correspond to an x power 1 term. This one is going to be the constant term, and this will be the remainder. So we can state our quotient pretty much by doing this. Quotient is going to be the 12x plus 34 here and here. Then finally, remainder will be just this 71 coming from right here. And that finally does the whole thing for us. So synthetic division, I assure you, is always extremely, extremely fast. This is one of those rare cases where, you know what, we could even bring example 4 right here. I think we have enough space to solve this one even. But first, any questions at all, folks, with that third example here? Okay, let's try this all over again then. So we're going to divide using synthetic division. That means we have to look to the divisor, and this is the key number right, that x minus 5. That negative 5 is going to be converted to a positive 5. Put in a little box here, and now we're just pulling these coefficients. There's something really nasty about this problem. Has anyone spotted the trickiness here about those coefficients? Or hang on, I thought there was something tricky, but no, it goes 4, 3, 2, 1. I thought 1 was going to skip. Sorry, my bad. It looks like we have no skipped values here. That will come up in the next section. But if, say, this 12x squared wasn't here, we still would have to put in a 0 for that 12x squared. But it looks like this one's not so bad. Let's put in negative 1 from the negative sign, 3, 12, negative 14, and 20. We have 5 numbers altogether. That makes sense if it's degree 4. Then we'll throw in our little bar right here. Next thing that happens guaranteed each and every time is that negative 1 copies down to that location. Now we're ready to start the process in earnest. Any questions at the moment, folks, before we give this one a try? Okay. So first thing that happens, this multiplies here. So it's just 5 times negative 1. And we record the result right over here into the new location. So now we have a negative 5. These two we're always just going to add up. So our next result right below is going to be a negative 2. Then that's going to produce a new value right here. Anyone see what the new value should be right at that red dot? Exactly. That 5 over here in the corner is always multiplying the numbers in the bottom. So here to here, negative 10, just as you said. Then we just add them up. So this is going to give us a value of positive 2. And it's really just rinse and repeat. 5 multiplies this 2, gives us a 10 over here. This location, negative 14 plus 10, will give us a negative 4. Then come down, 5 multiplies that negative 4, gives us a negative 20. And the upper right location here. Finally, add these together, and we get a value of 0. So that value is going to be a remainder. The divisor, that was just the x minus 5, this whole thing right here. I probably should highlight that. Hey, that kind of messes up the blue. But that's our divisor. And our quotient is going to be found by just pulling out those numbers and including the variable x. Well, any questions so far, folks, before we go ahead and state that answer? Yeah, go ahead. Oh, that's a great question. Pretty much here's how I usually kind of think of it. Our first coefficient for that negative 1 came from an x power 4 term. We're dividing by x power 1. So this one should be of degree 3, just 1 less. And that's usually the pattern that you'll see on all of these, since we're only dividing by x power 1. Other questions so far? Okay, so I'll state the answer like they said. I want to copy this down just to emphasize we're showing something is now equal to something else. So that whole thing, the original question, is now equal to the quotient. We put in that x power 3 just as a reminder. This will be negative x cubed. Here will be minus 2x cubed, or excuse me, x squared. They drop by 1 power each time. This will be plus 2x. This is the constant term, so just minus 4 without x's. And it's plus a remainder. This looks really weird, but they wanted that specifically, so follow it to the letter. There's your remainder of 0. Divide by the divisor, which was x minus 5. So following the instructions to the letter, this is how the answer is meant to come in. If you wrote your answer this way, that is definitely the better answer. It simplifies to just that. So let's say here, this whole thing is equal to negative x cubed minus 2x squared plus 2x minus 4. And that means we did it, folks. This one would take a long time to get through with ordinary long division. It's not so bad, but with all that methodical and tedious writing, I'm just inflating the chances of making a silly mistake somewhere in that process. This is the real meat and potatoes of the division algorithm. You're really just doing that with the coefficients, and it gets you to your answer right away. But also, there's one weird takeaway about this. The reason we do this kind of division is we want to solve equations. So now if you take this negative x power 4 plus 3x cubed plus 12x squared minus 14x plus 20, multiply both sides by x minus 5, clearing out the denominator. It will clear off this denominator, but that's 0 either way. You'll get x minus 5 multiplying the negative x cubed minus 2x squared plus 2x minus 4. So the moment we found a remainder of 0, the division was even, but division even means you really found a way to factor this thing. If this was set equal to 0, we would have already found one solution. X equals 5 from right here. Factoring gets you a solution to when things are set equal to 0 immediately. So in some weird way, long division is about solving this where there's no division set equal to 0. It's showing us how to factor it and giving us a solution right away the moment we factor. But that's kind of the spiel of what section 5.5 is all about. Examples 1 through 4, in particular, example 3 or example 4, are going to be the major things we're going to use to solve those equations. Well, any last questions, folks, before we call it a day? Okay, I think this is definitely a good stopping point for us. So we'll come back next class. In next class, our goal is to start section 5.5. But I feel like with where we ended today, this is going to be a pretty long section. This problem is not too bad, but I want to take time talking about the remainder theorem, the factor theorem, the rational zeros theorem, and so on. So I'm going to make an adjustment right here. I feel like an exam 2 really should end at section 5.4. 5.5 being the most technical section in chapter 5. We really should have more time actually solving it, doing a quiz on it so we can get real practice. So I'm going to make some revisions when we come back next class. And we'll do a little bit of 5.5 so we don't get behind on the schedule, maybe about a half an hour to 45 minutes worth. Then we'll turn into reviewing mode after that for the rest of the class. I'll bring a new document here and we'll review on that document. Well, any last questions, folks, at the moment? Okay, well, have a great day, folks, and see you all on Thursday's class.